Hello, and welcome to Lesson 30 of this Introduction to Differential Equations with Wolfram U. After reviewing some concepts from matrices, linear algebra, and systems of algebraic equations, we will now shift our focus to systems of homogeneous differential equations. As we will see, both the solution methods for a single homogeneous differential equation, as well as concepts from linear algebra, will be indispensable when solving systems of homogeneous differential equations. Let's take a look at an overview of this lesson. This lesson will be the first to introduce systems of differential equations. For the purpose of introducing systems of differential equations, we will limit ourselves to a simple case where each differential equation in the system is homogeneous with constant coefficients. We'll see that the behavior of solutions to systems of homogeneous differential equations with constant coefficients will depend on the properties of the eigenvalues. That is, if they are real and distinct, repeated, or complex. We will also see how to visualize solutions to homogeneous first-order differential equations using a stream plot such as the one here. We will begin by focusing on systems of first-order differential equations of the form here, where A is the standard coefficient matrix we've encountered in previous lessons, while capital X is a vector of variables. As an example, consider the system of differential equations here. The capital X vector would hold the variables little x and little y. Capital X prime is a vector holding the derivative of little x and little y. The coefficient matrix A has rows corresponding to the coefficients of each term on the right-hand side. We will see that tools like the direction field and stream plots we've encountered at the beginning of this course can be utilized to obtain qualitative results for these types of systems of equations. The method to solve systems of first-order differential equations with constant coefficients involves generalizing the methods we've applied to second-order linear equations. We will begin by assuming that the solutions for x of t and y of t are both exponential functions. We can then write the capital X vector with this assumption like this. Substituting into the system gives this matrix equation describing the system of differential equations. As a reminder, the A matrix is given here and is determined from the coefficients of the x of t and y of t terms in the differential equation. We can now evaluate the derivative to get this equation. The exponential term is common in each element of the vectors, so we can cancel that term, giving us the matrix equation here. The equation we found on the previous slide can be simplified by moving everything over to one side and factoring out the AB vector. We can recognize this equation to be exactly the same equation used to calculate the eigenvalues of the matrix A. Therefore, the AB vector is the eigenvector, with the constant r being the associated eigenvalue. We will now see how we can apply linear algebra techniques to solve systems of differential equations. To show how we can use the method discussed on the previous few slides, consider the system of differential equations here. The capital X vector is the vector of variables and has components of x1 and x2. We would like to first plot the direction field to get a qualitative understanding of the behavior of the solution. We will then find the general solution in the next example. We can first write down the two equations in the system of differential equations explicitly. The first row of the A matrix implies the equation here, while the second row gives the equation here. We will use streamplot to visualize the direction field for the system. The list in the first argument of streamplot contains the right-hand side of these two equations. The streamplot function then uses these to solve the system to generate the local direction field at a particular point. We can see in the plot that the solutions will all tend to diverge away from the origin. Now that we have a qualitative understanding of the behavior of the solutions, let's find the general solution to the system of differential equations and plot a few of the solution trajectories. We will begin by assuming that the solution is of the form of an exponential, where r is a constant and t is the independent variable. Substituting this into the system and canceling the exponential functions leads to a system of algebraic equations. Defining the matrix A from the coefficients in the system of differential equations, we can calculate the eigenvalues. The values for the AB vector are the corresponding eigenvectors. We will now substitute these eigenvalues and eigenvectors back into the assumed form for the solution to get an explicit expression for the general solution. Now that we have the two eigenvalues and eigenvectors, we can write the two solutions. The first solution is obtained by using the first eigenvalue, written as lambda1 here, and the first eigenvector, written as v1. In a similar way, the second solution can be written down using the other eigenvalue and eigenvector. Now that we have an expression for the two solutions, check the Wronskian determinant to see if these two solutions form a fundamental solution set. Since the Wronskian is never zero, these two functions do form a fundamental solution set. Therefore, the general solution to the system of differential equations will be a linear combination of the two solutions we just found. Let's compare the result we found with the result using dsolve value. The arbitrary constants chosen by dsolve value are somewhat different, so the form of the result is a little different. But after rearranging and redefining the constants, or by using initial conditions in the problem, it can be seen that the two solutions are in fact equivalent. To visualize the trajectories, use parametric plot for various values of the constants. We are only viewing the trajectories when the two constants are equal to 1 or minus 1, but we can see the general behavior observed in the stream plot when using these values, in that they eventually diverge away from the origin. When we solve second-order linear differential equations using the characteristic equation, we had to consider three cases about the nature of the roots of the characteristic equation. In a similar way, the eigenvalues of the coefficient matrix determine the behavior of the solution to a system of differential equations. If the eigenvalues are real and distinct, then all of the eigenvectors are real, and these eigenvectors, together with their associated eigenvalues, will form the solution set for the system of differential equations. If some of the eigenvalues are repeated, then we will still get a full set of eigenvectors, so the eigenvalues and eigenvectors will still form a fundamental solution set. In the case that the eigenvalues are complex, we will still get solutions in the form of exponentials, but with complex valued exponentials for the terms that have complex valued eigenvalues. Let's now solve the system of three differential equations defined by the matrix equation here. We would like to find the general solution as well as plot a few of the solution trajectories. Like we did before, assume the solution takes the form of an exponential. Since we have three equations in our system, we are using an eigenvector with three components. As we did in the previous example, our goal is to find the eigenvalues of the matrix which correspond to the value of r in the solution. We can then use the eigenvalue and the associated eigenvector to write the components of the general solution. Begin by defining the coefficient matrix, then calculating the eigenvalues of that matrix. Calculating the eigenvectors of the matrix gives the values of the elements A, B, and C corresponding to each eigenvalue. With the eigenvalue and eigenvectors found, we can write the general solution. Using the eigenvector v1 and the corresponding eigenvalue lambda1, we can write the first component of the general solution. The same can be done for the second and third components. Finally, check the Wronskian to verify that these three solutions form a fundamental solution set. Since the Wronskian is non-zero, the functions do form a fundamental solution set. Therefore, the general solution can be written as a linear combination of these three functions. Now that we have the general solution, use parametric plot 3D to visualize a few of the trajectories for various combinations of the constants C1, C2, and C3. The solutions are seen to take a trajectory similar to the solutions we saw in the previous 2D example, where the solutions tended to eventually diverge from the origin. The same can be said of the 3D example here, where the trajectories eventually diverge from the origin as well. We have learned in this lesson that solving systems of differential equations can sometimes be reduced to solving for the eigenvalues and eigenvectors of the coefficient matrix. When R is an eigenvalue and V is a corresponding eigenvector, the solution to the system of differential equations was seen to take an exponential form given here. The general solution is then a linear combination of these exponential functions for all of the eigenvectors and their associated eigenvalues.